Thanks for oh wow, that's a lot of hands. Thanks for inviting me to ChapelCon. I have never talked at ChapelCon, so this is going to be new. Can folks see my screen?
We
Uh,
can, yes.
okay, cool. Let me get all this Zoom stuff out of the way. It changed shape. And now the Zoom, hold on. Now the Zoom stuff is up there. Okay, great. I think it's good. All right. Yeah, so I'm the lead for the Spack project. And I think, as Brandon said, folks are reasonably familiar that Spack is it's a package manager for HPC. It's it was a project that was really started out of, I guess, rage at the state of building things on HPC systems, and so it's our attempt to try to make that easier. And the big thing with Spack is that the packages are parameterized, so you can easily tweak and tune the configuration. You can install specific versions of things. You can build with different compilers, and it actually configures your build and the build of all your dependencies and it gets things installed. So you can customize, say, what MPI is available or what MPI you want to build with. And increasingly, we're getting into dev workflows and helping teams actually build software, like some of the other package managers do, but basically helping them manage their dependencies and build against them during development, not just for deployment. This has really traditionally been the use case for Spack. The user base is pretty diverse. There's lots of different types of software developers. There's people who work in sort of DevOps, helping teams. There's administrators, there's user support staff, and then there's sort of end user type people, data scientists and computational scientists. And I think this is one of the things that makes Spack development difficult is that the community is so many different people. The same tool has to work for, say, a system administrator deploying a giant combinatorial stack on an HPC system, or a developer managing a bunch of dependencies for their code, or somebody who just wants to run something. So we're trying to sort of navigate the space between all of these different um, roles. And it can be kind of hard because software management is different between the different areas. We also serve a lot of different workplaces. Obviously, the DOE labs, because we sort of originated there. Spack started, I guess, in 2013 at Lawrence Livermore, but it's grown since then, as I'll talk about later. But we also serve the Office of Science labs. I don't know why there's so few of them in this latest iteration of our survey. Usually an NSA and Office of Science are pretty on par with each other, but we got less of a response rate this year. Other public research labs, universities, and then actually the sort of cloud and industry contingency keeps growing year over year. So that's encouraging. The project is more than just the package management tool. It's kind of this thriving, or I don't know, very busy ecosystem. And so there's a fairly large community around Spack. I think we have something like 1,500 contributors at this point, if you count all the contributions to the package repo. And so that's sort of the foundation. And then there's a core tool that a smaller number of people work on, but that's still pretty active. And the biggest part is the sort of 8,500 or so package recipes that people are constantly maintaining that are changing all the time on GitHub. And what you may or may not see is that there's a bunch of CI infrastructure behind this as well. So there's a whole team at Kitware that maintains CI for the project that makes sure that at least a subset of these package recipes are building all the time. So on every pull request that you submit, we'll go and see what changed, and we'll farm those jobs out to both like machines at University of Oregon and also machines in Amazon. The CI is sort of half and half, cloud and on-prem. And all of this stuff enables people to build different software stacks, different customized software stacks for their particular domain on top of Spack. So E4S is one you may have heard of. It's the sort of DOE's. It was the sort of canonical software stack for ECP. Amazon has a stack that they like to build for their cluster deployment. So does Microsoft actually. Livermore has its own stack internally, and then each application is sort of its own software stack with custom dependencies and so on. So it enables people to sort of shape their software world and maintain things, at least somewhat more easily than they used to when they had to build all this by hand. Spack, it has three main goals. Like I said, we want to build the core tool, the CI infrastructure, and the package ecosystem, but we can't sustain the package ecosystem ourselves. So one of the goals from the start of the project has really been to grow adoption. Started out with sort of telcons that we opened up to anybody. which was, I guess, novel at the time. I think a lot of projects are doing that sort of thing now within DOE. Um, and we want to get people using the tool so that we can turn them into contributors. And so, without this pipeline, where people are picking up Spack, using it, and continuing to contribute to the package ecosystem, we're kind of dead in the water because we just don't have the resources to make sure that 8,500 packages stay up to date. So in that sense, the Spack package ecosystem is a lot like a software distribution, like say Red Hat or Debian or one of these Linux distros. It's maintained by this large community of contributors, and a lot of what we do is focused on at least trying to make their lives easier, trying to make contribution easier, and trying to make um, people want to stick around. So it's 12 years old at this point. The community has grown quite rapidly since I started. So like I said, I started like in June 2013. You can barely see the contributions on the chart from that period. And this is showing lines of code in the Spack package repository over time from like 2013 up to 2016 when I first started making these charts. And you can see, I guess we presented this at SC15, so that's why there's sort of an uptick here. That presentation sort of sparked a bunch of people to start contributing to the project. And I guess it had reached a certain level of maturity at that point. We actually originally open sourced it in 2014, but then maybe this is when we got the word out. Anyway, lots of orgs started contributing at that time. And if you plot out this graph every year, I mean, it kind of starts to look the same. And this is the latest iteration of it that I've done. I haven't actually done one for 2025 yet. Sorry. But if you look at the size of that original set of contributions on the contributions now, you can see like there's almost 300,000 lines of code in the package repository for Spack, and those contributions from the early days are just this little tiny sliver of the graph, and we've got lots of different orgs contributing. So we're trying to manage that. ECP's over, but Spack continues to grow. It's actually used at least, or at least people view the documentation in all of these places here. I don't have a good sense of how many total users there are for Spack, other than like it's probably thousands. But this is the aggregate sort of doc view count from 2023, and you can see that there's not that many countries that don't have at least some Spack users or someone pinging the website, I guess. And so we started asking, how do we grow the project from here? How do we broaden adoption even further and make the project more sustainable? And that's what sort of led us to Linux Foundation and HPSF. I guess around the end of ECP, a lot of projects were thinking about how they were going to sustain themselves into the future because the funding was sort of coming to an end, and Office of Science and other parts of DOE were considering, how do we sustain this software stack that we built under the Exascale project. And so we actually started conversations with Linux Foundation before that, like in December of 2021. And we just sort of played around with the idea of like, what would it look like if Spack went into a foundation, and what does that mean? One of the things that we wanted from that is we wanted a neutral project home. And I think, that's something that Chapel wanted as well. We really want people not to feel like this is just Livermore's project. We want people to feel like they own a piece of it and that they can contribute and that they have a stake in its evolution. And so and the goal there is again to get more participation. So that was one of the goals. We also wanted a way to fund project activities, things like continuous integration and user meetings and so on. And so we talked to Linux Foundation and learned about their sort of basic requirements. And so if you do this, and I guess Chapel has, or if you're considering this for another project, you need a technical charter, which is really sort of the like ground rules for your governance. You need the governance to be open, and then you need to give your trademark or whatever rights you have in it to the Linux Foundation so that they can protect that. This one's interesting because I find that people do not people know about copyright because your license fundamentally deals with copyright. They might know about patents because some of the licenses deal with patents. But trademark is one of the last little sort of IP assets that people don't seem to know about for open source projects. And really, like it ends. I've found through this process of starting HPSF that it really fleshes out places where you might think that nobody wants an ownership stake in the project, but someone actually does. So we've had projects where, like maybe a university owned the trademark for the project and they charged people for exclusive use of it. And so we were like, well, we can't bring that into an open foundation. And so I found this rule to be actually pretty useful. For some projects, it's very easy. You just sign a piece of paper that says like, "Hey, we don't have any stake in the trademark." And for others, it's been complicated because lawyers have to get involved. Some lawyers aren't used to giving away trademarks and so on. But I do think it's an increasingly important um, piece of IP for a project to control. You may have seen like some of the drama around the Rust trademark policy, or I don't know if people have used Jenkins for CI. Um, Maybe you remember the days when it was called Hudson, well, which was like around 2000 before Oracle bought Sun. But there was a lot of consternation around the trademark for the project that led to it being renamed from Hudson to Jenkins. So look those up if you want to understand, you know, things that can go wrong. So anyway, we joined forces with Cocos mainly because Spack and Cocos were two of the more, I guess, adopted projects within ECP that had sort of a community vibe to them. And the goal was really to leverage that to start a larger umbrella under Linux Foundation, and that's what eventually became HPSF. Um, we sort of built the foundation around this idea that we wanted to enable performance portability, which is really one of the main goals for ECP. It's kind of something that Spack and Cocos have in common, and that really the modern HPC um, ecosystem has in common. And so we wanted to leverage the fact that these two projects at least had, they built communities that were working to some extent, and that people were familiar with them to sort of bring on more projects and start mentoring them into to also have larger communities. And so at this point, I think we have like over 10 or 12 projects in HPSF, or at least in the process of joining, including say Chapel. And it's been good. I think it's started collaboration. We have a home for things, and we ran the HPSF conference last year, which actually brought 204 people together. And I thought the vibe was really good because it it wasn't your usual HPC conference, which HPC conferences are great, but they tend to be very kind of academic. Like here's a new paper, there's an emphasis on novelty, and what we wanted with HPSF Con was a place where people could talk about like building things. And so the fact that one of the things that we did with HPSF Con is that it hosts user meetings for member projects as well as the broader sort of plenary sessions. And so just having all of these projects user meetings got some really sort of low level technical people together and able to talk about what's really going on, like getting into the weeds of what's happening on their projects. Which I don't feel like there's a venue that specifically focuses on that other than like say your ChapelCon or meetings like this. So that's one benefit of HPSF is we will co-host the member meetings. What else does it mean to be a Linux Foundation project? So we have a legal entity now. So if we needed to have money that was just for Spack, we could do that. And so under Linux Foundation, at least most of the legal entities are a 501c6, which is like an industry consortium. Some of them are like more charity focused, and so they'll be 501c3s. But the main thing is that it's a neutral legal entity that's not controlled entirely by one organization. And I think that's been very useful. We have a technical steering committee now, and we've made the sort of developer meetings more public. So the steering committee meetings are open. And we have governance documents now. Those are sort of finalized, and we've worked on more formal contributor onboarding docs and things like that. Like I said, the trademark got assigned to the Linux Foundation, and then things like the website and the GitHub organization, which you would need if like something happened to the leadership of the project. Those are basically Linux Foundation becomes co-owners of them, and so you have to give those over as well. And they're not like administering your GitHub organization. They actually don't really take much of an active role there at all. The goal is so that if something were to happen in the project, they could start it back up. They would have the assets, and it wouldn't just get sucked into whatever internal source control the owning company has if they decided to take it private. Broadening the steering committee has been actually good. It's given us a chance to bring in people who maybe aren't even core contributors, but have a stake in the project. So like Mark Paterno at Fermilab leads the team that does a lot of contributions to Spack. But he hasn't done that much development himself. But having him as like someone who really understands what the users need there and what their teams need for development has been really useful. And so I'd say like this whole setting up the steering committee has enabled us to sort of broaden the set of people who have input into the project, and that's been really useful. HPSF, for anybody who is interested in that, or is interested in joining, it looks kind of like this. There's a governing board, which really manages the finance, and there are committees off of that, like events. So HPSFCon is a committee off of the governing board. Outreach is a committee off of the governing board. This is like events. This is events and marketing, things like that. We're trying to spin up a training effort within HPSF, and then the technical governance for the sort of umbrella is separate. And that's sort of a core principle for Linux Foundation, is that the financial and the technical governance are separated, because they don't really want, people to just buy into a project and be able to say where it should go. It's not like they can't influence it. They can certainly talk to the TAC and say, here, we'd like to do this, or here's a priority for us. But the technical priorities are set separately by a different body. And I think that's been helpful. The technical projects all have their own governance in addition to sort of HPSFs. They're not bound to HPSFs. They can make their own decision about what to do for their projects. And so it's not like you join this and all of a sudden you lose autonomy for your project. You have to have sort of a thriving project. The goal of the TAC for HPSF is really to mentor these projects and help them sort of grow to larger levels of maturity. And then the TAC also manages a bunch of working groups, which are intended to be sort of collaborative activities that cross-cut different projects. So we're working on building like a CI service for HPC, something that you could just install an app on GitHub with, and then have your project have access to, say, GPU runners and things like that. So we're working on that. And then continuous benchmarking is something that we're also looking into, having a set of benchmark suites that use the projects or that are related running all the time. So these may grow software artifacts that then become technical projects as well. But we're trying to be a home for more than just the projects themselves, but also the collaborative activities that span them. So the hope is that HPSF will help these projects grow their community, find common needs with other folks, and then join these working groups. We have this life cycle that we built for projects that's supposed to be sort of the plan for for growing the community. It's emerging is designed to be really easy. So if you want to join HPSF, the criteria for emerging are not much different than the criteria for becoming a Linux Foundation project. It's basically be able to be a Linux Foundation project and be aligned with the sort of mission of HPSF. Established is supposed to be a larger project that has contributions from maybe one organization sustained, and where the governance could be just one org, but usage by multiple organizations. And then core is really designed to be this is the aspiration, right? Is where your project has contributions coming in from multiple places, so that if one of them went away, the project could be sustained. So that's sort of our progression. I think the reception within the community has been pretty positive. We ran user surveys. We asked before we joined HPSF what people thought of this idea, and it seemed like people were mostly positive. So like in 2021 and 2022, I think over half of people said they probably or definitely would like it if we joined the Linux Foundation, and then some similar but smaller percentage in 2022 said they thought it was a good idea. We asked again after, and we said, hey, has our transition into Linux Foundation given you more confidence in Spack? And it seems like 50% of the community has said yes. I guess 10% said no. I don't think that means they got less. And then 39% said not sure. So I think this is pretty good in general. 50% of people are positive on it, and then a lot of people, it doesn't really affect their opinion. All right, so that's sort of the community aspect of the project. I'm going to talk a little bit about our road to version 1.0, because it's been a very long journey within Spack, and this is the more technical part of the presentation. If you look at what we set out to do, we're really trying to parameterize builds for tons of HPC projects that care about low-level details, like say what compiler they're using, or can we build this large application with multiple compilers and with lots of packages that have different requirements. And getting to something that we could consider 1.0 has been a pretty long and involved effort just because of the complexity of that. When we started, we built a dependency resolver, we call it the concretizer, that was not complete, and which means that it would often say that it couldn't find a solution to dependency graphs for which there was one. And so we wanted something complete that actually could search the full sort of NP complete space. People complained initially with Spack that it was always sort of rebuilding fresh from the latest versions of things. And it turns out that's actually kind of a hard thing to do without a nice solver. And so we wanted reuse of existing installations. So that if you already have a reasonable version of CMake installed, that we'll use that instead of building the latest, greatest one with like, epsilon difference on the patch release. We wanted stable production CI so that we were actually keeping projects built all the time, a binary cache for that. And then the big things that we've been focusing on in more recent years have been compiler dependencies and separating out the package repo so that essentially the package ecosystem can live separate from Spack. The two were coupled for the first 12 years of Spack's life. And that was okay because it let us move pretty fast in terms of how we supported core features and packages. But it also means that there's a little less stability for users. Like if they want to go back and load, say, a package repo from last year and have it work again with the latest version of Spack, there could be API breaks. We tried not to have them, but we weren't making any promises. And so with that, we had to make a stable package API so that this coupling between between the core tool and the built-in repo, so that we could split them out and have some interface to build that around. So, this whole compiler dependency model and the stuff that went into 1.0 is pretty much the biggest change that we've ever made to Spack. We basically gutted the dependency model. We took a concept that we had in Spack from the beginning, which was compilers, and we turned it from, say, a node attribute, where like every node says I'm built with like GCC at a particular version or Clang at a particular version, and we worked it into the dependency model in a much more general way. And I'll talk about what that means. But this is a picture of me in 2018 talking about how simple this was all going to be. It turns out it took about 7 years after that to get there. So it's been a pretty long journey. So for the solver, the reason that we need a new solver, a new concretizer for Spack, is really because there's a whole bunch of conditional logic that started growing into the packages. We basically wrote a DSL for the packages that was more expressive than what we could actually model in the solver. And so when we started getting things like GPUs, there are all kinds of constraints on GPU packages. So the CUDA package here, there's a ROCm package analog to this. It has a variant called CUDA that's on or off, tells you whether you're building with CUDA, simple enough, right? Well, if you have it on, you need a dependency on CUDA, so we can express that. And if you have it on, you also need to specify what the architecture is that you should build for the GPU. So this variant is actually conditional on that one. This one doesn't exist if that one doesn't exist. So we had to build support for sort of conditional variants in. And then there's a whole bunch of constraints for what version of CUDA supports what compiler. So you can see like down here, there are all these conflicts with different GCC versions, different Clang versions that are really based on like what language level different versions of CUDA support, and also on, I guess, NVIDIA's support matrix. But this is a very abbreviated version of the list of sort of architecture and compiler compatibility for CUDA. And so we had all that in a sort of superclass, but we really needed a better solver in order to manage all of these different conditional constraints. The solver has a pretty large task laid out for it in Spack. There's all these contributions coming in all the time, changing package.pys constantly. Each of the package.py files has constraints in it. There's also constraints that come from like Spack core, from the build systems, and from developers who can express preferences in packages.yaml, from users, and from the command line. So we take basically all of those constraints and we throw them in one tool, which is the concretizer. And its job is really to find a graph that matches all the constraints. So it turns out that's NP hard. We looked into ways to do this, and initially we thought we were just going to write our own solver in Python. It turns out that is multiple people's life work to write an efficient NP complete problem solver. So we looked at different paradigms for doing this, and we settled on answer set programming. ASP is pretty nice. I don't know if folks are familiar with it, but it's sort of a dialect of Prolog, or at least the code looks that way. It's not Turing complete like Prolog. It actually, you take your ASP program and you boil it down from sort of first order logic into propositional logic, and you throw that in a SAT solver. And so it's expressing sort of a limited domain of problems, but it's what we need for our dependency resolver. And so what used to be a bunch of really complicated Python code we took and we turned that into something that just spits out a bunch of facts, throws them in the solver with this sort of, was 700 lines, is now probably like 1,200 lines of ASP code, and comes back with a consistent graph for you. And so the heavy lifting is done by this C++ component, which is Klingo, which is the ASP solver that we're using. And this is kind of what the programs look like. Like this is what the output of Spack would be that we pass to the solver. I'm not going to get into all the details of ASP here, but if you're familiar with Prolog, you have rules where if you have node lamps, node CUDA, you have a variant on this thing that's enabled or disabled, and you have a dependency from lamps on CUDA, then you can derive that the dependency has to be a node in the graph too. So, for example, if you have node lamps and lamps depends on CUDA in your graph, this rule would derive the fact that CUDA node needs to be there. And you read them backwards. I don't know how that evolved really. I think this thing is supposed to be an arrow. If that looks like an arrow to anyone, the Prolog people thought that is what an arrow looks like. So that's where that comes from. You take this thing where you have variables, you basically instantiate these rules with every sort of propositional thing. So the capital things are variables, the lowercase things are just facts or like things that are true. And you instantiate the rules with all of these sort of propositional logic components, and you get a completely propositional program and then solve it. And so for this problem, if you have A depends on, you'd have a graph expressed this way where these are the possible dependencies. These are the two possible solutions. You can have B depends on D, or you can have A depends on B and C, and B and C depend on D. So that's basically what we're doing. And ASP is kind of cool. It searches for what they call stable models or answer sets of the input program. So unlike Prolog, where you basically express all this logic, and then you can do queries and you can say, hey, is this true? Is this true? Is this true? And it goes and unifies all the rules and tries to figure out if the thing you asked is true or not. With ASP, you're basically getting all of the solution sets. So you're getting these stable models, which are basically sets of facts for which all of the rules in the input program are idempotent. So they're fixed points in the solution space. And so that's basically what we're searching for. And it turns out that maps, or at least we think it maps really well to the dependency resolution problem. It makes the modeling problem a lot easier because ASP is just way more expressive than what we could do in Python or what we could do with a regular old SAT solver. So we rewrote the concretizer, but we had this optimization problem where the concretizer still didn't go and try to reuse existing installations. So if you had, say, LLVM built with a slightly older version of CMake, it would rebuild the whole thing because it would say, oh, there's a newer version of CMake. So I clearly have to rebuild all of this stuff. And so using sort of a Spack installation over time was somewhat painful. And we did have some reuse, but it looks sort of like this. If you have a Spack graph and you're going to go and resolve that, we basically hash every node and come up with a configuration hash for it. And then Spack would say, okay, well, does that hash exist or not? And this is very sensitive to, say, if like libelf changes, then the hash is going to get propagated all the way up the graph and say, like, all these things need rebuilds because I've got a new version of this other package. In many cases, if you were going top down and you said, hey, I have MPI leaks, it has a couple constraints on the call path installation it wants to use. Could I just use the one that's installed? It would be fine. And we could ignore solving all this stuff down here. We could just reuse whatever other hash is installed. But we wouldn't see that because we're just asking for, here's the resolution, what's the hash? So we modified the solver to basically tell it about all the installations and all the binaries up front. So what that looks like is this. We have to say, hey, there's an OpenSSL installation. It has this hash. If you use this hash, then you have to fulfill all of these constraints too. So it's version 1.0. It depends on this particular dependency with this particular hash. It has this compiler version and so on. And so everything needs to be consistent with those things if you end up using this particular hash. Turns out that ends up being a fairly easy problem to express, at least at a high level in answer set programming. You can basically just say, hey, if a package is a node in the graph, then you can basically pick one hash out of all the installed hashes for that package. and you use it if you want to, or you don't have to pick anything at all. So that's what one's the upper bound. There's no lower bound, and you're just picking one hash from this set of installed hashes. If you pick one, you have to impose all the constraints that it requires, and then you just say if you haven't picked a hash for something, then we have to build it. And then you tell it to minimize builds. So ASP is nice because it does this sort of multi-objective optimization thing where you can say, minimize this objective function in the solution. And you can have tons of criteria for that. So this was nice when we got this working because previously, like I said, if you tried to build, say, HPF5, you get a graph that looks like this where it says, oh, I need to rebuild all of these. And users were like, well, why do I have 6 Pythons on my machine at this point? If you use the reuse, then it says, oh, CMake 3.21.1 is fine. I do not need to use 3.21.4. I can just use the one I have. And a lot more stuff gets reused, and you only have to build a few things. And so users were fairly happy when we came out with that. So meanwhile, to really support compiler dependencies and also to support the Python ecosystem, we needed a way to model graphs that did not have one version of every package. If you look at other package managers and how their dependency resolvers work, there is often an assumption that for a given node in the graph, you're only going to have one version of that thing. And Python, people really, really love to pin their build dependencies, and the package manager doesn't really deal with build dependencies at all. And so you essentially build the thing and then put it into the graph, and it ensures that that final runtime graph is fine. But it doesn't impose any constraints on build dependencies. And so we were being a little too tight there with how we modeled things. For compilers, we wanted the same thing because we really wanted to model a compiler's dependency, but we wanted people to be able to build mixed compiler graphs. And so essentially, the build dependencies need to be able to vary between nodes, but things like the runtime dependencies needed to be consistent throughout the runtime graph. And so we had to introduce that concept of Spack. You can see here from this graph that bad things can happen if you don't allow multiple versions of build dependencies, especially in the Python ecosystem. So here, like GP2 depends on PyGEvent and NumPy. It turns out that the latest version of gevent is like 30 or something like that, but this is version 1.5. And the reason for that is because NumPy requires a really old version of Cython. And so gevent, the version that we could find, or that Spack could find, that supports this version of Cython is like 1.5, so like 30 versions back. And so what you really want to do is split out this graph so that there's a unified part where basically like there's only one thing allowed of any given node. And then there is, a non-unified part down here. So this guy can be built with Cython 3, and this guy can be built with Cython 0.29. So this problem took us a very long time to solve because if you model this recursively, if you say that this is a unification set, this build dependency can be different, and it has its own unification set. It has its own dependencies too. And this guy over here might have a different set of dependencies. And so if you actually model that out, you get exponential explosion in the total number of unification sets in your graph, and it blows out the ASP solver. So we tried, dynamically splitting the graph when needed to do this. We basically went from a node ID that had just a package name to a node ID that had a package name and a number for like the duplicate ID, where we could just sort of instantiate duplicate IDs on the fly. And the solve time went from, much greater than 2x in some cases, and worse for even larger graphs. So that wasn't going to work. And so we had to push real hard to find an encoding where we didn't get this explosion in the set of in all the unification sets. We did find that by eliminating cycle detection in the solver and using it, that we could get a lot more performance, but we don't want cycles in our graphs. So we went and met with the people who built Klingo, and it turns out they have some native undocumented feature that actually handles this. So we moved from sort of ASP level cycle detection to inbuilt cycle detection, and we're able to remove this overhead. And to get rid of this sort of unification set problem where these things recursively explode, we merged all the unification sets for build dependencies, except for in cases where we needed like many, many of them. So like for some packages, like setup tools are allowed to have many versions, but their dependencies are all sort of unified as well. And we sort of cut off the recursion so that the grounder and the sort of setup phase of the solve wouldn't explode. Once we did that, and once we did a bunch of other optimizations, we were able to get the solver back down to about the same performance that we had before we introduced this feature. And I guess you could look at that sort of two different ways. You could look at that as, gosh, your solver could have been way faster for a really long time. Or you could look at it as, hey, we were able to provide all this extra functionality for about the same performance. And I like to look at it the latter way, but we are constantly looking for ways to optimize the solver. I think there's a lot more in there, so I'm not giving up yet, but it's a battle to make sure that your NP hard problem continues to perform well for most cases over time. Um, the other thing that was tricky about this is we thought about models that were maybe simpler from a like code complexity perspective. And one of the things that we thought about doing was, hey, just put the burden on the packager, have them add constraints to their packages that maybe know about multiple versions of build dependencies or things like this. When we tried these sort of decoupled models, we got bad solutions, and there really are cases where, like the build environment, certain things about the build environment affect the run environment, and particularly like for compilers. Like if you want your compiler to require, say, a particular runtime library for the thing it's building, that's a way that the build environment affects the run environment, and so there are constraints on versions there. And so without a fully coupled model, we really couldn't, build something that modeled software as it was. We would have something that was really hard to think about and that didn't, solve the problem for anybody. So it took us maybe 5 or 6 iterations over some number of years to get something that worked here. So we're pretty happy when we got something that performed. Um, the next challenge for 1.0 was language dependencies. And one of the reasons that we wanted compilers as dependencies was because sort of original Spack assumed that every node would have a C compiler, a C++ compiler, and a Fortran compiler. And that's not really true for Python packages. So you've got sort of extra useless metadata on some of those nodes. And also it means that those languages are special. There's a lot of knowledge in core Spack about C, C++, and Fortran. And we'd like to have support for, say, like Chapel or other languages where there might be multiple implementations. And so in 1.0, languages are virtual dependencies. And so you depend on C, and Spack finds you an implementation of that thing based on what provides it. And so you have to add these dependencies to your package. But we have this extra layer of abstraction in there that I think is going to allow us to do a lot of exciting things going forward. So like if you remember all the constraints on the CUDA packages, a lot of the compiler constraints are really just dealing with language levels. It's like Intel compiler supports C++14 at this version, and GCC supports it at this version. And with this, I think we can move a lot of those constraints to just be, I need C++14, or I need a variant on like one of these virtual dependencies. And the user doesn't have to know what compilers support that. Spack can just know that, or the compiler package can know that. So we're sort of moving the concerns to a place where they make more sense. The other cool thing with this model is that it enables us to separate these sort of different unification requirements for build dependencies and run dependencies. So if you have zlib, and this is a fairly simple package, right? It has a C and C++ dependency, and those are both satisfied by GCC if Spack picks GCC. It could be Clang there as well, but you're basically satisfying these dependencies. It's got a build dependency on gmake as well, which has a build dependency on C, so you get GCC there as well. And then the interesting thing about the solve in 1.0 is we actually let the compilers tell you what additional dependencies are required for the thing that they're building. And so we first find a compiler for zlib. We ask the compiler, like, what runtime libraries do you need? And it gives a set of constraints for that. And so we inject these runtime library nodes for C and C++. So GCC runtime provides libs and C++. glibc provides C. This is currently a virtual or an external dependency, but we're hoping that we can get Spack building from glibc up. at some point. And those satisfy the C dependency for everything. And the interesting thing about this is that the injected dependencies over here, they're linked dependencies. So you've got a build dependency that says, hey, your runtime graph has to have this link dependency in it, and that has to be unified in the sort of unification set for the stuff that is that's built into the runtime environment. And so that works out really well because if you have mixed compilers, like if I had the Intel compiler in here, Intel compiler depends on GCC for its runtime library. And so we can actually unify the GCC runtime node here and ensure that the Intel compiler version used is consistent with, say, the GCC that gets used. And that's true, for a number of the vendor compilers. They rely on libstd C++ for their runtime. So we're sort of getting down to the lowest level where we actually can guarantee consistency for these types of things. We would eventually like to be able to choose implementations of libc. It's a little trickier to get the build mechanics working for that, so it's not done yet. But we're pretty happy with this model for 1.0 for compilers. And I think the other cool thing with this is that it means that pretty much anyone could put a new language into Spack. They just have to put, the thing that provides the language in, like say the compiler, and they can model the runtime libraries in addition to that, and they can maybe model, compiler features like OpenMP and stuff properly, as opposed to as sort of this like node specific concept where we're not modeling the constraints that say the OpenMP version or the C++ version imposes on other things in the graph. So we're getting closer to sort of a model of software, how it really is. We introduced tool chains in 1.0. I don't want to get too much into the specifics of that, just because I want to leave time for questions. But basically, this lets you set up an alias for a set of compilers or a set of compilers and libraries. And they can be conditional. So you can say, like, I want Clang G4tran, which is basically Clang plus G4tran, and you don't have to lie to Spack anymore. In the original version, you would have to basically say, like, this is Clang, but I'm just going to slip a Fortran compiler or a different Fortran compiler in here under the hood, so that users can actually compile the way they want to. Now we can actually model that, and the dependency graph will model both. Compiler configuration is a little different, and then this is probably more of a I don't know, as much of a social problem or a sort of maintenance problem as it was a technical problem. We wanted to split out the package repository, and so this was an interesting exercise because there's so much history in the original Spack repository. There's over 8,500 package recipes, and we wanted to factor that out into another repo so it could be maintained separately, and so that you could even get rid of the built-in Spack packages and only use the ones that matter to you or your own ecosystem. That is hard because anytime you have something coupled with the repo, there are a bunch of sort of assumptions that creep in that people don't notice on pull requests. And so we had to go through and find all the places where Spack just couldn't operate with the separate built-in repo, places where the core was too tightly coupled with what was there. So we did this gradually. We started syncing the core, the main Spack repo with a separate Spack packages repo on GitHub, so that on every push to the main repo, when people were contributing, we would sync all those changes over to the sort of external Spack packages repo. And then in a branch, we sort of modified Spack so that it would use a separate package repository and found all the things that broke there, got the test passing. And then finally, we were able to sort of cut over at the end, but not after a bunch of things were revealed about sort of the tight coupling between the two things. Build systems, which are really superclasses for our package DSL, they used to live in core, and it's really not the right place for them because they, whether you have a CMake package or an AutoTools package really depends on whether anything's going to use them. And they are sort of, they affect sort of the build mechanics of the package. So they really belong over in the package ecosystem. So we sort of moved those into the package repo. That was fairly complicated. And that actually gets sort of all of the package ecosystem pieces mostly in one place. There's like a few little places where we left things more coupled, but I think we did okay on this. We had to define, or at least I guess we didn't have to, but we wanted to define a stable package API. And this is another one of those places where, Spack's been around for like 12 years. And there are certain aspects of the package API that I guess are, there are calls in here that are more um, complicated or, maybe not the greatest calls, not how I would have done it if I'd have done it from scratch. But we basically just went through and looked at what packages we're calling and wrote that down. And we patched out all the things that we thought were just too horrible to have in a package API. But we left what we had. But we documented it and we're saying like, hey, we're going to support this. If you have packages that were built for, a particular package API version, they will work on any version of Spack that supports that. And we may we may add features to the API over time, but the goal is really that future versions of Spack will have backward compatibility with the original sort of 1.0 cutoff, or that's the hope. So we've documented that. You can actually find the package API. It's documented here in the docs. Right. And I talked about this already. One cool thing with the new version of Spack is you can actually, sort of like you would with a GitHub action, say, hey, here's a repo. It lives at this Git URL, and you can clone it to that commit. So you get sort of an extra measure of reproducibility there because you can actually pin your package versions and not move them forward over time like you had to when you sort of pulled the original Spack repo. We're trying to expand on this and have more sort of references to things. Like we want to be able to include an environment in sort of the same way. But that's more of a 1.1 or 1.2 feature. And finally, one thing I wanted to mention is we actually we added concurrent builds to 1.0. And this was something that wasn't actually on our original list. But we had we had an intern who was very adventurous, and she got this working. We actually hired her, and she was able to rework the sort of core package scheduler for Spack so that we can now have concurrent builds of different packages on, say, on the same node. And this actually, I think it's good in 1.0. It can speed up your build. We didn't make it the default because it kind of screws up your output, but in 1.1, we're going to have support for Gmake's job server for both for Gmake and for Ninja. And so you may be able to get some really fast builds going with this once that's there, because that enables the different package builds to dynamically share parallelism. So I'm pretty psyched about this. So anyway, if you want to try it out, there is a -p option on Spack install that'll say this is how many packages I want to build at once, and so you can get that going and hopefully get faster builds. All right, so that's about it. Oh, sorry, I didn't revise this. Let me just fix it up right now. And yeah, if you want to join the Spack community, we're a project in HPSF. It's neutral. You can even come to the governance meetings, to the technical steering committees meetings that are once a month. And we have a Slack instance. This is probably the best place to go. There's like 3,800 people on Spack Slack with constant discussions over there. So join us there, or just submit a pull request and let me know if you have questions.
Awesome. Thanks, Todd. Let's end everyone. Beat me to it. Don't even have to ask for the round of applause. Do folks have questions? Okay, Brad, go ahead.
Yeah. I have questions, but I also want to make clear that I know how to find Todd if I need to. So if somebody else has questions, please raise your hand. But Todd, just to start off with kind of a social one that was on my mind during your talk. So I would say that my experience, and I'm wondering if you have had a similar experience as somebody developing kind of novel open source software in HPC, is that you run into a lot of grumpy people who are grumpy about a lot of things. They tell you why it's not going to work and blah, blah, blah. And I was curious, like if that's at all true, what kinds of rocks do people lob at Spack, and they're grumpy about this, or they don't like this, or it's not going to work because of this, and how justified versus simply misinformed or not understanding are they, would you say?
I tend to think that there's like a lot of truth to most people's complaints about something, right? Like, I mean, some people have been entirely unreasonable. Like when we first set up a matrix instance, we got a guy in there who showed up and told us that Spack was just inferior Nix and we should delete the whole project and use Nix instead. And he ranted for a long time about that. And so then we learned how to use mod controls on Matrix, and we blocked him. So, but that was sort of the only like completely, troll level complaint that I think we've gotten. Um, lots of people, I mean, I think have complained about, justifiably things in Spack that don't work. Some of them are in the room with us right now. And I what I try to do for that I find, works at least a little bit is, I mean, I try to keep people aware of the roadmap, and say like, look, we don't do that right now. It's not great, but we're planning to fix that in version X, Y, or Z. I actually spent a lot of time this year making like a 5-year roadmap for Spack, which dwindles out after like 3 years or something like that. But and slotting that into releases, and so I'm hoping to get that put into GitHub milestones, so I can actually like point and say like, this is when we're thinking we're going to do this. If you want to help this along, you could grab that issue. I find that works better, and I try to kind of coach the maintainers on this. Like if somebody asks a question like that and you just say like, no, we don't do that, that's stupid, like then it tends to cause fights, and because they don't feel like you're valuing their opinion, right? Like, and I mean, I don't know. I found that if I respond in a more positive way to the people who complain, the grumpy people, then a lot of them are like kind of apologetic about being grumpy in the first place, which actually is useful. And I don't know. I think that's just like open source. Like I don't want the Spack community to get to the point where, we're having constant like infighting, and it's not a pleasant place to be. I think we benefit a lot from having, I don't know, like a more mature community of people who've taken the time to get to become computational scientists, which is different from like, I don't know, a lot of the NPM ecosystems where like, just like a much broader community of developers contributes, and I think the fights erupt more readily there. But and so I think like in some ways, we're lucky because we have a community that's used to, I don't know, pain because they're in HPC. So we get away with stuff for that too. Anyway, I don't know. Does that answer your question?
Yeah. Thanks very much. And I'll let somebody else go and go back to the end of the queue.
Michael, you beat me. Go ahead.
Okay. Hi, Todd. My question maybe is one of those annoying questions, but when I interact with these different sort of package managers like Spack or Homebrew, I'm always just fretting about like, well, what's going to happen the next time something like that XZUtils thing happens? And I just wanted to know, like, do you see Spack as having any role in providing for some kind of guarantee that the package is hosted in an ROK, or is that completely the user's problem?
Both. I mean, I think it's going to be hard for us to ever say that like we're guaranteeing the supply chain security of all 8,500 packages in Spack. And I mean, I don't know. I've talked to our like security people at Livermore, and they're just like, yeah, we're going to be fighting this supply chain thing for our whole lives because it's very, very hard. But on the other hand, I mean, there are things that we do. So, I mean, we automatically check like the checksums when a maintainer commits to Spack, and we enforce that everything is checksum, but some other package managers actually don't do, which is somewhat shocking to me. Which it's not the greatest measure of security, right? Because like you could get a malicious person contributing something, but you're
Right.
banking on the fact that most packages are not compromised most of the time. And so if you record the checksum at contribution time, you've got that. We are adding actually this year, we got some new funding for supply chain security. So we're going to add SBOMs to Spack and try to do scanning on a continuous basis and have NVD identifiers on the packages. So that at least we'll know about CVEs. Although to some extent, like CVEs are not my biggest concern in an HPC world. I'm more concerned with stuff like XZ. So I guess we did avoid the XZ compromise in Spack because we're slow and we had not shipped that version. And then we did not ship that version, so there's that. But I think like there's a constant tension between shipping the latest version of things as fast as possible and security, right? Like I don't exactly know how best to mitigate that other than doing more scanning. which I think is the best thing we have. We are going to add, I think, along with SBOM, like serif scanning and things like that. But I don't think that would stop the XZ vulnerability, honestly. Like if XZ gets released and it has something malicious in it, to some extent we are trusting the projects themselves. And so I don't know. I think there's a larger solution to that than what package managers could provide. I mean, on the
Yeah,
other hand,
it almost seems like to solve that problem, we have to get all the package development to be trustworthy and then certify that in some way. And this is going to be nearly impossible. But anyway, we should let somebody else ask a question. But thanks for your
one
thoughts.
more thing on that, I guess I can say is we're requiring that we, at least on Spack, that we know the people who, or at least that we can like trace them to an institution. We don't have anonymous people with merge privileges to develop. And I know, like, I think that's good. Some communities do object to that because some people are anonymous for, like, I don't know, because they don't want their online lives to conflate with their personal lives, or they've been harassed in some instance in like their personal lives and they want to be anonymous online. So I think we could probably come up with something where we verify them ourselves for that. But
Right,
there are tensions.
that doesn't apply to like a package that you would build though, right? Like the source code for some package that's hosted in Spack will be, like if it's glibc or something, it's whatever they do is whatever they do, right?
Yeah, that's right.
Anyway, thanks.
Awesome. Well, that means I'm next. Woohoo. So I have like the same question for directed both at like HPSF and at Spack, like in those two contexts. I'm just curious if there's like parts of the HPC ecosystem that you want to see, or that you'd want to see like more growth in terms of like more, for example, like, I don't know, performance analysis tools or something like that, like within each of these different domains, like if there's places where you would like to see growth.
Yeah, I mean, we have HPC Toolkit and HPSF, but I'd like to see more performance tools for sure. I mean, I started out as a performance tools person. So you're not going to get me to say no more performance tools. Yeah, I mean, performance tools are always kind of underserved, right? Like they don't get a lot of funding. They're not on anyone's critical path necessarily until they are. And then, they may not be tested as much as you'd like them to be because they weren't on the critical path before. So I think it would be great to foster more, CI and things for performance tools. So they actually have, and I mean, we had this discussion on an HPSF TAC once, more problems than most packages for CI. So for example, like I know that HPC Toolkit can't just use your standard cloud instance for a lot of their performance measurements because the VMs disable the CPU features that they need. It's similar for GPUs. So like they're in many cases there are even more like requirements that they have that make life harder for them. So I empathize.
Awesome, thanks. I think Brad, back to you.
All right, Michael asked a security question, which was one of my other ones, so that's great. The other question I had was, so when I first heard about Spack from you, I asked a question that I think a lot of people probably ask you, which is like, do we really need another package manager, particularly an HPC specific one? And you gave the argument for why. And hearing you talk through the challenges with respect to your March to 1.0 today, it made me wonder, have any of the problems that Spack solved or the things that you've done had an influence on package managers outside of HPC where like you've been able to pass some of your good ideas on to them, or they've realized like, oh, we would be better if we did what Spack was doing? Or we kind of like isolated in our HPC space and that kind of cross-pollination hasn't occurred?
I think some people dismiss us as kind of weird in HPC, but I do know that like, have you seen this WheelNext initiative in pip that's going on right now, or in Python? There's a guy at NVIDIA, and there's the UV people, the astral.sh people who are building sort of the UV. It's a pip alternative. They were inspired, at least in part, by what we did with ArchSpec, which is like we spun ArchSpec out of Spack in hopes that like the easy build people and others would use it. And actually Conda uses it now. But it's a library for modeling microarchitectures and compatibility. And so like you detect the microarchitecture on the host. That's why Spack Arch tells you that you're on like a Cascade Lake. And we know what binaries are compatible with that architecture. And so they're trying to use that for Python wheels. They have a model that's inspired by it to some extent. for both CPU and GPU. So I'm a little jealous because I'd like to get us to have a better GPU model in that regard. So there may be some feedback between WheelNext and Spack based on what they did. But yeah, I think that has caught on in other places. I know I can't think of any other direct ones other than the fact that environment modules started allowing at in their syntax because people were used to Spack versions. But we stole that from like other package managers, so I don't really have any claim to at.
Cool. Oh, even the one example is very cool that you gave for Wheel. So, all right. Thanks very much.
Awesome. Okay, and that is